Good afternoon, everyone. In the last lecture, we were discussing about the frictional forces, right? In this lecture, we'll be discussing some of the important concepts. Like we'll be discussing about the spring forces, how actually spring forces act on an object, and we'll be also discussing the frames of reference. Here we'll be discussing both inertial as well as non-inertial frames of reference, and how do we actually apply different things or the laws of motion to the non-inertial frames, right? So before switching to that topic, we'll just discuss this problem here, right? Briefly, a block of mass 2 kg is placed on an inclined plane at an angle of 37 degree, right? With the horizontal. The coefficient of friction between the block and the surface is 0.7, right? What will be the frictional force acting on the block? What is the force applied by inclined plane on block, right? So we have to find the frictional forces, friction force acting on the block, as well as the force applied by the inclined plane on block, right? So this is the block here, right? You can see here uh, the weight of this block is mg. This is in the downward direction, right? Weight of the block is in downward direction, mg. We can resolve this mg into two components. One is vertically, that's mg cos 37 degree, right? And this is the horizontal component here, that's mg sine 37 degree, right? So this is sine component and this is the cosine component, right? This is sine component and this is the cosine component here, right? So the block is static, right? The block is static, right? Let's see whether the block will be static or not. It depends upon the amount of the friction that acts on this block, right? So if we calculate the limiting value of this frictional force, the limiting value of frictional force will be equal to mu into n, right? Mu is given as 0.7, and you can see that since there is no vertical motion for this block, it means that the normal reaction must be equal to mg cos 37 degree, right? Mg cos 37 degree, right? Mg cos 37 degree. And we know that if this angle is a 37 degree here, right? 37 degree, then this has to be 3, this will be 4, and this will be 5, right? Then cos of 37 degree will be equal to cos 37 degree, it will be equal to 4 upon 5, right? It will be 4 upon 5, correct? So we can replace the value of cos 37 degree by 4 upon 5. That will be mg 4 upon 5, right? 4 upon 5. So this is the value of the normal reaction, right? This is the value of the normal reaction. Now the question is, what's the value of this limiting friction? It will be mu times n. That's 4 mg upon 5, right? 4 mg upon 5 will be the value of this normal reaction, right? And the value of mu is given as 0.7. It will be 0.7 multiplied by 4 multiplied by the mass of object, that's given as 2 kg. And let's take the value of g to be equal to 10. So it will be 10 upon 5, right? 10 upon 5. So it will be 60, right? It will be actually, or we can write it as 28 into 2, that will be 56 upon 5, right? 56 upon 5, right? So it will be almost, so this is our, okay, this will be 11.2, right? That's the 11.2. 11.2 will be the value of this limiting friction. So a maximum value of the static friction here is 11.2 newtons. So this will be the maximum value of the limiting friction, right? And let's this friction will act in the horizontal direction along the inclined plane like this, right? Now we have to calculate the value of this mg sine 37 degrees. Sine 37 degree here from this triangle will be nothing. It will be actually equal to 3 upon 5, right? 3 upon 5. So 737 degree is 3 upon 5. So we can replace. So we can calculate the value of this mg sine 37. That's equal to, the value of m is 2, the value of g is 10, right? And 37 is 3 upon 5, right? So it will be 3 multiplied by 4. That will be equal to 12, right? That's equal to 12 newtons, right? That will be equal to 12 newtons, which means that if the external force is equal to 12 newtons, if the external force is equal to 12 newtons, or we can say mg sine 37 degree is actually greater than the limiting value of the friction here, right? It's greater than the limiting value of friction because mg sin 37 has a value of 12 newtons, and the limiting value of the friction is having a value of 11.2 newtons, right? Which means that the block will slide down this incline, right, with some resultant acceleration, right? And the maximum friction here in this case will be the value of the limiting friction, right? So the frictional force, static friction, will be here in this case equal to the limiting friction, that will be equal to 11.2 newtons, right? 11.2 newtons will be the value of frictional force, right? Now we have to find what is the force applied by inclined plane on block, right? Inclined plane on block. So there are two forces because of the inclined plane, right? One is the frictional force and another is the normal force, right? And it is perpendicular to this plane, right? So there will be net resultant force by this inclined plane. Let's call that as F, and that F will be the resultant force by the incline. That will be equal to under root of n square plus frictional force, that will be Fl square, right? Fl square. So if we substitute the value of n, right, and we know that Fl is actually mu n, so it will be n square plus mu square n square here, right? Or we can write it as n under root of 1 plus mu. So this will be the value of the contact force or the force applied by the inclined plane on block, right? You can substitute the value of mu here, that's 0.7, and you can calculate the value of n from this equation, right, to get the value of the total net contact force by the inclined plane on block, right? Now let's discuss the same thing here, the contact force, right? So contact forces are the forces applied on the block, right, by the surface in contact, right? When the surface is in contact, you can see there we are applying an external force on this block or on the system. This is the F external force, right? And it's along the horizontal direction, and you can see if block just starts to move in the horizontal direction, then there will be definitely a static friction along this, or there will be a frictional force, right? There will be a friction force. Now there will be two forces because of the surface here, right? Two contact forces. One will be the normal reaction, right? One is the normal reaction. One is the normal reaction. Another is the frictional force, right? Another is the frictional force. So two forces are there, normal reaction and the frictional force, right? And the normal reaction, we know it's always perpendicular to the surfaces in contact, right? These two surfaces are in contact, and perpendicular to this surface, there is a normal force N here, right? And this is the frictional force in this direction, right? This is the friction force in this direction, right? And this is the normal reaction. That's equal to N, correct? That's equal to N. And this is the net resultant force or the contact force here. That's what we call as FC, right? FC is the net contact force. And this, since frictional force and the normal reaction are perpendicular or normal to each other or perpendicular to each other, the net contact force because of the surface in contact will be given by FC, that is equal to under root of frictional force, that's F square, and the normal reaction square, right? And the normal reaction square. So this is what we call as the net contact force on the block by the surface, right? Now there is a term, there is a concept what we call as angle of friction, right? Angle of friction. Now in case if this friction is equal to the limiting value of the frictional force, if this friction on this block is actually equal to the limiting value of the frictional force, in that case what happens is that we define a term what we call as angle of friction. So angle of friction is nothing, you can see there, you can see here, this is the limiting value of the friction, and this is the normal reaction, and this angle is the lambda here, and this angle lambda we call as angle of friction. So we can say angle of friction is nothing, it's the angle between limiting value of the frictional force, right? Angle between the uh, a normal reaction, right? Angle between N and net contact force, right? Net contact force, right? When limiting friction acts, right? So the maximum value, when there is a maximum value of the friction force between the two blocks, or we can say that at the point at the angle of friction, the block just starts to move, because at the angle of friction, the frictional force between the block and the surface is maximum. That's equal to limiting friction, and that angle which the resultant force makes with the normal direction we call as angle of friction. So we can say that uh, at angle of friction, the block is at the verge of starting the motion, right? It is at the verge of starting the motion. So angle of friction will be here. That's the lambda here. If we calculate the tan of lambda from this portion, right? If we calculate the tan of lambda here, the tan of lambda will be nothing. It will be perpendicular upon base. Perpendicular here is FL, right? It's FL, right? It's FL upon the base. That will be equal to N, right? So FL upon N, that's the normal direction. And the maximum value of this limiting friction is mu N, right? Upon N. So N and N will get cancelled. So this gives us the mu, right? So it means that tan of lambda actually gives us the mu. That's nothing. That's the coefficient of friction, right? Coefficient of static friction. Coefficient of static friction. Coefficient of static friction. So using the concept of angle of friction, we can actually calculate the value of the coefficient of friction, right? Similarly, for the inclined plane here, right, you can see for the inclined plane, the friction is along this direction, right? And normal direction is along this direction. This is the angle of friction, right? And this is the net resultant, what we call as resultant contact force, right? Resultant contact force. Now, if we calculate the tan of lambda for this case, tan of lambda for this case, inclined plane, it will be equal to, once again, frictional force, that's FL upon the N, right? FL upon N. So this will be the value of what we call as tan of lambda, right? FL upon N. So FL upon N will be the value of tan of lambda. And we know FL is nothing. FL here on an inclined plane is mu N. Mu N. And N on an inclined plane is nothing. It's mg cos of theta, right? Mg cos of theta. So we can substitute the value of once again here. So it will once again give us the same thing, right? Tan theta is equal to mu N upon N, right? That will once again give us the coefficient of static friction, right? Coefficient of static friction. So with the help of what we call as angle of friction, we'll get the value of the coefficient of static friction, right? So at the angle of friction, the block is at the verge of starting the motion, right? Or we can say the frictional force acting on the block is the limiting friction, right? So let's try to see this problem right here. You can see a horizontal force of 49 Newton is just able to move. So the question is saying is just able to move. We said that angle of friction is the angle at which the block just starts its motion or is at the verge of starting its motion. The same statement is given here. A horizontal force of 49 Newton is just able to move a block of wood weighing 10 kg on a rough horizontal surface. Calculate the coefficient of friction, right? And angle of friction. So a horizontal force is there, right? We'll just draw the diagram here. This is the block, right? And block is of mass 10 kg. Block is of mass 10 kg, right? A horizontal force acts on this block that's equal to 49 newtons, right? 49 newtons. Is just able to move a block of weighing 10 kg on rough horizontal surface. There will be a frictional force on this block, that's FL, in the backward direction. At this point, when the block just starts to move or starts its motion, the value of the friction will be the limiting value of the frictional force, right? So 49 Newton is along the horizontal direction, right? It means that if the block just starts its horizontal motion, then this 49 Newton must balance the limiting value of this frictional force. It must balance the limiting value of this frictional force, or we can say the limiting friction here is 49 Newton, right? Now, this is the frictional force, right? This is the frictional force, and this is the what we call as the normal direction, right? And this is FL vector, right? This is normal vector here, that's N, and this is the resultant contact force. This will be the resultant contact force between the two, right? This is the FC, and this is our what we call as angle of friction, right? Angle of friction. This is the angle of friction. right? We have to calculate the coefficient of friction and angle of friction, right? Angle of friction. So the coefficient of friction will be, we know the tan of lambda will be here, that will be equal to FL upon N, right? FL upon N. FL upon N. That's equal to, the value of FL is given as, that's 49, right? That's 49 upon N, right? That's 49 upon N. And this has to be equal to mu, right? This has to be equal to mu. Since there is no vertical motion at all, right? You can see that there is no vertical motion. The block moves horizontally. Then the force of the normal reaction force will be balanced by the weight of this block, that's mg. Or we can say that N will be equal to mg. M is given as 10. So it will be, value of G will be taken as 10. It will be 100. So 100 newtons will be the normal reaction here. So tan of lambda will be here. Tan of lambda will be equal to, tan of lambda will be equal to 49 upon 100. That will be equal to 0.549, right? 0.49 will be the value of tan of lambda, and this will be the value of coefficient of friction also, right? So the value of static coefficient of static friction is 0.49, or lambda, that's the angle of friction, will be tan inverse of 0.49. So this will be the value of angle of friction, right? So we calculated both coefficient of friction as well as angle of friction, right? Now let's talk about the spring forces, right? Spring forces. So whenever you can see here, let's suppose we have a, let's suppose this is the spring block system here, right? This is the spring block system. And this spring is in a relaxed state, right? Relaxed state. When the spring is in a relaxed state, there will be no force along the string, along the spring, right? There will be no force developed along the spring, right? So we can say that the force along the spring here in the relaxed state will be actually equal to zero, right? There will be no spring force, right? Now the question is that let's give a small extension or compression to the spring. Let's extend it a bit by some small extension, right? We're extending this spring by a smaller extension, right? Now, because of the extension of the spring, the restoring force that gets developed, right? We are extending this spring, right? If we release this block, then the block will try to regain its original position, right? The block will try to move towards its original position once again after the extension when the contact is actually removed from this block, right? So it means that actually there's a force, right, which we what we call as restoring force, right? Whenever extension is done in the spring or compression is done in the spring, the restoring force gets developed in the spring, and that restoring force try to regain the original position and shape of the spring, right, continuously, right? And that's force we call as spring force. This force we call as spring force, right? And this force is always away from the point of contact, right? You can see here the block here is this is the point of contact here, right, between the block and the spring. So the spring force here will be away from this point, right? That's Fs. So this is the direction of the spring force. Similarly, spring is attached here at this point on this wall, right? This is a wall here. If we attach a spring at this point, right, then the wall must also feel this force, right? Wall must be experiencing this force as well, right? And we know that this force will be away from this point in contact, right? This is the point of contact. And here, this will be the direction of the spring force, right? This will be the direction of the spring force, right? Now the question is, how do we actually calculate the value of the spring force? It was given by the Hooke's law, right? Hooke's law. So Hooke's law said that within the elastic limits, right, the force developed in the spring is proportional to the extension in the spring, right? It's proportional to the extension in the spring, and opposite to the direction of this force is opposite to the direction of the extension, right? So we can write F is proportional to, if this is the extension, right? If delta x or x is the extension in this spring, then the force will be proportional to minus x, right? And we can replace this proportionality with some constant, that's k, right? So spring force will be equal to minus kx. Now this k we call as spring constant or stiffness constant, right? Spring constant or stiffness of a spring, right? Or stiffness of a spring. So this constant tells us about how stiff actually is a spring. It means how easier or how hard it will be for us to extend a spring by a small extension, right? So if the spring constant is greater, it will be very difficult for us to extend a spring, right? If the spring constant is less, then it will be very easier for us to extend a spring by a small extension, right? We also call it as stiffness of a spring, right? Stiffness of a spring. So K is a spring constant or stiffness of a spring, right? And we can see the direction of this spring force is always opposite to the direction of the extension, right? Or the compression, right? So this is the value of the spring force. And if we plot the force between force and x, right, it will be a straight line, right, with a negative slope, right? You can see here we have plotted the force versus extension, right? And the graph is a straight line passing through origin, right? Passing through origin with a negative slope, right? So the negative slope actually signifies that the spring force always tries to restore or regain the original shape and position for the spring, right? So let's try to solve this question here, right? You can see here we have two springs, right? Two springs are connected. One spring is connected to the block of mass 1 kg, right? Another spring is connected to the block of mass 2 kg, right? Now the question is that where to find extension in both springs if the system is in equilibrium. So you can see here there are two springs like in this system, right? So we have to find the extension in both the springs when the system is in equilibrium. Now let's assume the system is in equilibrium, right? The net force on all the blocks 1 kg and 2 kg is 0. And at equilibrium there is some extension in both the springs, right? Let's suppose in this spring the extension is x1 and in this spring the extension is x2, right? Extension is x2, right? Now the question is that if we study the equilibrium of this block, right? This block will be in equilibrium only, right? This block of mass 2 kg will be in equilibrium only if the weight of this block, that's mg in the downward direction, is balanced or it's actually cancelled out by this spring force in the upward direction, right? We can see that we know that the spring force here will be away from the point of contact, right, with this to the block. So this will be the Fs, right, spring force here. Now to balance or to keep this block in equilibrium, this Fs must be equal to weight of this block, right? Weight of this block, that's mg, right? That's mg. And we know that force developed in the spring must be k times x, that x is the extension, that will be equal to mg. M is the mass of this block, that's 2 into 10, taking the g value equal to 10. So the extension x2 net extension in this second spring will be 20 over k, right? 20 over k. The stiffness is given for this spring as 100, so it will be 20 over 100, right? Or we can write it as 1 over 5 meters, right? Or we can write it as 20 centimeters, correct? So 20 centimeters will be the extension in this spring, right? 20 centimeter extension is in this spring at equilibrium, right? At equilibrium. Now the same question is for the 1 kg block, right? We have to find its equilibrium condition, right? For 1 kg block, there are two spring forces, right? There are two spring forces. There are two spring forces for the 1 kg block. This is the 1 kg block, right? And this is the first spring below, and this is the spring above, right? Now both the spring will be applying a spring force on both the contacts of the block, and for this contact, it will be in this direction, Fs1, and for this contact it will be Fs2 in the downward direction, and there will be weight of this block also, that's mg in the downward direction, right? So to keep this block in equilibrium, so Fs1 must be equal to weight of this block plus the spring force Fs2, right? Fs2, correct? And Fs1, let's suppose extension in this spring is x1, right? Kx1, right? Kx1. Mg is the weight of this block, that's 10 plus Fs2. Fs2 we have already calculated, that was equal to Kx2, right? Kx2, and the value of K was equal to 100, right? That was equal to 100. At x2 was equal to 1 over 5, right? 1 over 5, or we can say 20 Newton. So this will be equal to 30. But the extension in the first spring is actually equal to 30 over K. The value of K is 100, or we can write it as 30 centimeters, right? 30 centimeters, correct? So it's very obvious that the extension in the first spring will be more than the extension in the second spring, because for the first spring there are two forces in the downward direction. One is the weight of the block, and another is the spring force because of the second spring, right? So the extension in the first spring must be greater than the extension in the second spring, right? So x1 has the value of 30 centimeter and x2 has the value of 20 centimeter, right? Now let's discuss another question, right? Find initial accelerations of A and B respectively when string is cut, right? You can see here we have two blocks of mass, each of mass m and m here, right? Two blocks of mass, each of mass m and m here, right? And there is a spring connected to this mass of block B, right? Block B to block B, there is a spring connected directly to the block B, right? And the block A and B are connected by a string, right? Now the question is that what will be the acceleration of the system, right, when the string is cut, right? Initially the system was in equilibrium, right? There was an equilibrium established for this system, right? Now suddenly what we do is that we just cut this spring, right? Now let's see the situation before equilibrium and after equilibrium, what's going to happen, right? So for the equilibrium of this block, the tension in this string should be equal to the weight of the spring, right? Weight of this mass block. So the tension in the string is equal to mg, right? That's equal to mg. You can write T is equal to mg, right? And the same tension, we know that tension is a pulling force, so it always pulls a block body or point at the point of contact, right? So it will pull this block of mass m here in the downward direction, right? So there are two forces in the downward direction. One is the tension, another is the mg, right? So let's suppose Fs is the spring force in the upward direction. At equilibrium, this spring force will be actually equal to mg plus t, or we can write this spring force at equilibrium is equal to the value of t is mg. It will be 2 mg, right? It will be 2 mg. So the value of spring force is 2 mg, right? Another question is that what will happen suddenly to the system if we cut this string, right? If we cut this string. Now when the string is cut, the string becomes slack, the tension in the string becomes zero, right? If the tension in the string becomes zero, there is no contact for this block of mass m. It will only fall under the force of gravity, and the acceleration of this block will be nothing. It will be acceleration due to gravity, that will be g, right? So g meter per second square will be the acceleration for this block in the downward direction, right? For this block, the acceleration will be g in the downward direction for block A, right? But the question is, what is the acceleration of sudden acceleration of this block of mass B, mass m, block B, right? When the string is cut, at the time when the string is cut, the tension becomes zero, right? T becomes zero, and the forces on this block at that instant will be mg in the downward direction. And we know that at that instant there is a spring force that's 2 mg in the upward direction, right? 2 mg in the upward direction, right? 2 mg. So the net force on this block now will be F net will be equal to 2 mg minus mg, right? 2 mg minus mg, right? That will be equal to mg, right? So the acceleration of this block will be actually equal to g, right, meter per second square. But this acceleration will be in the upward direction. Now it means that both the blocks will move with the acceleration of g, but the block A will move downwards with acceleration equal to g, and the block B will move upwards with the acceleration equal to g, right? So this is the scenario. So both the blocks will not move in the with the same acceleration. Uh, First block will move in the downward direction, and the second block will move in the upward direction, right? Now let's discuss different frames of references, right? So frames of reference, it's very important for us to study the dynamics of any body or motion of any body, right? So it's any reference with respect to which we are measuring the or we are studying the motion of a body, right? motion of a body. Let's suppose we have a Cartesian system, right? XYZ system here, right? And this is the origin, right? And if we measure the position or the velocity or acceleration of a body is studied with respect to the origin of this Cartesian system, then this Cartesian system becomes our reference, right? It becomes us our frame of reference, right? Now this frame of reference is majorly it's of two types. It can be of two types, right? This frame of reference can a movable frame of reference, right? It can move with a constant velocity, or it can be at rest, right? Or it can move with an acceleration as well, right? So according to that, we have two frames of references. One is inertial frame of reference, another is the non-inertial frame of reference, right? So with respect to inertial frames of references, any reference with respect to where observing the motion of a system or a body, right? The frame of reference which is either at a rest or is moving with a uniform motion, right? It's moving with a constant velocity, right? And that frame we call as an inertial frame, right? So this is let's suppose this is our Cartesian system. If this Cartesian system is at rest, right? It's at rest, right? Or this system is moving with some constant speed or velocity along this direction, right? Then this system will be an inertial system for us, or inertial frame of reference for us for the observation, right? Of motion or position of a body, right? Similarly, if the frames of references with respect to which we are studying the motion of a system or a body, which are movable, right, with an acceleration, right, which are moving with some acceleration, with some net acceleration, right, with some net acceleration. Let's suppose this is the same frame, right, and if there is some acceleration to this frame, right, in the horizontal direction, a is the acceleration, right? So we can say this frame of reference, right, is a non-inertial frame of reference, or it's an accelerating frame of reference, right? Let's suppose if a car is moving with some acceleration on the ground, right? For us, the ground is at rest. So the ground frame is an inertial frame for us, right? And similarly, if the car is moving with some acceleration in the horizontal direction, right? Then this frame, if we do any measurement with respect to this accelerating frame, so this frame will be non-inertial for us, right? So it will be an inertial frame. Similarly, if a system, if a let's suppose there is a body moving in a circular motion, right? If there is a body moving in a circular motion of mass m, right? If this body is moving in a circular motion and this body is in continuous rotation, right? It's in continuous rotation, right? So this body is continuously in a rotation, or we can say that the body is accelerating because the velocity of this body is changing at every instant, right? It's an accelerating frame of reference, right? So if any measurement is done with respect to the rotating frame, right? Rotating frames are also the accelerating frames, right? They are also the non-inertial frames, right? So these are the two types of references we study. One is the inertial frame, another is the non-inertial frame, right? For non-inertial frame, we have the acceleration, and for inertial frame, either the system is at rest or with a uniform motion, right? Or constant velocity, right? So there comes the concept of the pseudo force, right? To make, we know that Newton's law, to make the Newton's law applicable in non-inertial frames also, right? In non-inertial references also, we apply a force, fictitious force that we call as pseudo force, right? And if we are observing or calculating the uh, physical quantities with respect to the accelerating frames of reference, we have to apply the pseudo force also, right? The direction of that pseudo force will be opposite to the direction of the acceleration as seen by the ground frame, right? As seen by the ground frame, right? So that will be the direction of the pseudo force on the system, right? So let's apply the concept of the pseudo force for this on this problem, right? We can see a pendulum of mass m is suspended from the ceiling of a train moving with an acceleration a, as shown in figure. Find the angle in which pendulum is in equilibrium, at which the pendulum is in equilibrium with respect to the train. Also, we have to find the tension in the string, right? So there are two references. If we observe this system with respect to the ground frame, right? Or we can observe this system within its own frame also, which is accelerating, right? Which is accelerating, right? So you can see the train is moving with an acceleration, within a horizontal acceleration a in the horizontal direction, right? So we can observe this pendulum in two frames. One is the ground frame, right? Another is the what we call as accelerating frame. And with respect to this accelerating frame, this pendulum is actually at rest, right? Is actually at rest. This pendulum is actually at rest. It's having no motion, right, at all, but at an angle of theta, right? But with respect to the ground frame, that's an inertial frame, right? If we are observing this moving reference, right, the pendulum is also moving, right? The pendulum is also moving. We can solve this problem with respect to the ground frame as well as the frame of its in its own frame, right? So let's try to solve this problem in the accelerating frame, right? Since this is accelerating, right, with respect to ground, the acceleration is in the horizontal direction, that's A. Then we have to apply the fictitious force of opposite direction, right? That will be equal to mass into the same acceleration, but in the opposite direction, right? So this will be the fictitious force that will be equal to minus ma, right? Minus ma in this direction, right? This is the fictitious force or pseudo force in this direction, right? Now we know that with this frame, the pendulum is not actually moving at all. It's in equilibrium. So to decide the equilibrium for this pendulum with respect to this accelerating frame, we'll draw the free body diagram for this pendulum. In this accelerating frame, there is a force ma in this direction, right, for this pendulum, and there is a weight of this pendulum that's vertically downwards, right? That's mg, right? And there is a tension, right, at an angle of theta, right? Tension at an angle of theta. Now we can resolve this tension into two components. One will be t cos theta, t sin theta, right? This is t sin of theta here, and this is t cos of theta. T sin of theta, and this is t cos of theta. So t sin of theta must be equal to mg, right? That will be equal to mg. And t cos theta must be equal to ma for the equilibrium of this pendulum, right? Now if we divide both these equations, our tan of theta will be equal to value of tan of theta will be equal to uh, g upon a. Now the question here is, I have taken this angle to be a theta here, right? This angle be a theta. Now if we take this angle with respect to the originally given angle, right, then this theta will be actually here 90 minus theta, right? 90 minus theta, or we can take this as theta dash. Let me take it as theta dash. So theta dash here is nothing, it's actually 90 minus theta in terms of the given angle. So tan of 90 minus theta will be cot of theta, that will be equal to g upon a, right? G upon a. So cot of theta for this pendulum is equal to g upon a, right? Now for the same question here, similar question here, we have block placed on an inclined plane, right, on a wedge, right? And this block slides down the wedge, right? But the wedge is accelerating in the horizontal direction, right? With an acceleration equal to given as a. A is the horizontal acceleration for this block, right? For this system, a is the horizontal acceleration, and we have to find a condition so that this block remains at rest with respect to the wedge, right? It remains at rest with respect to the wedge. So what we can do is that if we try to solve this question with respect to the inertial frame, with respect to this accelerating frame, then we have to use the pseudo force as well, right? And the question will be easier for us to solve, right? So there will be a force mg in this direction, right, for this block, and there will be a contact force normal to this block, and there will be a fictitious force along the horizontal direction, right? That's fs, or we can write it equal to ma. That will be equal to ma, right? That will be equal to ma. So ma will be the fictitious force in the horizontal direction, right? Now to decide the equilibrium of this block of mass m, we have to resolve these forces into different direction, right? Into different directions. Let's suppose if this is theta, right? If this is theta, if this is theta here, right? Then this angle will be theta also, right? This angle will also be theta here. This angle is also theta. So this will be ma cos theta here, right? This is ma cos theta here. And if this is ma cos theta, then this has to be ma sin of theta. Ma sin of theta, right? Ma sin of theta, correct? And if this is ma cos theta, this is ma sin of theta. If we resolve the weight of this body as well, then the component along this will be actually mg sine of theta, right? Mg sine of. Since this system is in equilibrium, then this mg sine theta must be balanced by this what we call as ma cos theta component of this fictitious force, right? Fictitious force. Now m and m will get cancelled. We'll get the condition acceleration should be equal to g sine theta over cos theta, right? G sine theta over cos theta, or we can write it as g tan theta, right? So this is the condition for this block to be at rest with respect to the wedge. If the wedge moves with an acceleration of g tan theta, right, in the horizontal direction, then the block will remain at rest with respect to wedge, right? So that's it for today. We'll stop here. In the next lecture, we'll be starting with the circular motions, right? So till then, take care and goodbye.